Hi, everyone. This is Professor Moser. Just wanted to briefly go through a couple of the highlights of the Exam 3 practice sheet. There wasn't many students that attended the review session live, so I just wanted to kind of go through the quick notes version of this and kind of highlight some of the things that you have to know that are on this practice test for the exam. Again, the exam will be very similar to what you see on the practice test. I tried to put enough examples of each type so that any student that simply goes through what's on this practice test will be prepared. With that being said, the real exam will not nearly be this large. I try to only choose about one problem of each type, just so I can get a gauge of how much of that material that you learned. The first two questions kind of go hand in hand. They're all about graphing quadratic functions and some key elements of quadratics. The one difference between question number 1 and 2, though, is the way in which it's presented. So let me just kind of quickly go through this for you. Um, when we have a quadratic, there's two different types. There's those that open up and those that open down. To determine whether it opens up or down, it's based upon that leading coefficient a. If it's in standard form, then a is the number that's out in front of the parenthesis. In this case, it's a is equal to 1. If it's in general form, as it is here, then a is the coefficient of the x squared term, which again is going to be 1. In general, when a is positive, in other words, when a is greater than 0, those are when the quadratics are going to open up. And in terms of applications, any quadratic that opens up, its vertex is going to be a minimum value. On the other hand, if that a value is less than 0, those are the ones that are going to open down. And the resulting vertex would correspond to a maximum value. With a quadratic in standard form, it's very easy to look at it and see the value of the vertex. So if it's in the form a times x minus h squared plus k, in standard form, the vertex is going to be located at h comma k. So for this particular parabola, we can just visually look at it, and we see that the vertex is going to be at 1 comma negative 9. If the equation is presented in general form, then in order to find the location of the vertex, you need to remember the vertex formula. Okay, this is a very important formula that will appear on at least 2 to 3 questions on the test. For a quadratic equation presented in general form, we find the vertex by the following formula. It's a point, so it's going to be an ordered pair. The x coordinate of the vertex is given by negative b over 2a. Once you know the x value, you simply take that and plug it into the function f, and that output would be the y value of your vertex. Okay, so 2 different ways to find the vertex of a parabola based upon whether it's in standard form or general form. From there, the axis of symmetry of a parabola is always x equals the x coordinate of the vertex. So if you know your vertex is h comma k, the axis of symmetry is always x equals the x coordinate of that vertex. If our vertex is at 1 comma negative 9, for instance, then the axis of symmetry would be x equals 1. In part C and D, the methods are the same. If you're finding an x-intercept, then what you would do is you would set that function equal to 0 and solve. If you're finding a y-intercept, then that's a function evaluation. You would evaluate f of 0. Once you have the graph, you can very easily find the domain and the range from the graph. Alternatively, for a quadratic or for any polynomial, the domain is always negative infinity to positive infinity. This is for any polynomial. In particular, it's especially true of a quadratic. For the range, you can actually find the range without graphing these. if you know the way in which the quadratic opens, whether it's opened up or down, as well as by knowing the vertex. The moment we know that this graph opens up, we know that it's going to go towards positive infinity. So the maximum, there's going to be no maximum, so it's going to go all the way up. If we know that the vertex was at 1 comma negative 9, that y value of the vertex, which is negative 9, is going to be our lowest point. And so you can find the range from negative 9 comma infinity, not necessarily by needing to have the graph, although it certainly helps, but you can find that range by just knowing the direction that it opens, as well as the y value of the vertex. Question 3 is just another extension of this. It's the same kind of idea. You have a quadratic. It's in general form. So you're going to need to find the vertex. Notice that because a in this case is negative, that means that it's going to open down. And when it opens down, that means that the vertex will be a max value. To find the location and the value of the max, you need to use the vertex formula. Again, please make sure you know this. It's negative b over 2a, and then f of negative b over 2a. We then have an application problem that will require the use of the vertex formula. It's kind of your standard application type question. First thing you want to do is write a formula down. The picture will be given just like it is in the practice sheet. So write down a formula, express it using your single variable x, take your equation, write it in standard form. You will get some kind of quadratic that, based upon your a value, will either open up or down. And then when you're asked to find either the max or the minimum, once again, that's going to come down to using the vertex formula. It's negative b over 2a is the x value of the vertex, and then the y value, which is the given min or max, is found by taking the x value and plugging it into the function. The next thing we come to is general polynomials and what we call an end behavior. One of the things that we learned is that the end behavior of a function is entirely determined by its leading term. So if you can look at the leading term of a polynomial, let's suppose that it's a sub n x to the n. There are 4 cases altogether. The first one is based upon whether the leading exponent is even or the leading exponent is odd. If n is even, and if in addition the leading coefficient is positive, then your polynomial is going to go up to the left and also up to the right. On the other hand, if a sub n is less than 0, then the polynomial will fall to the left and it will also fall to the right. As an example of this, I always kind of like to think of like what the graph of x squared and negative x squared looks like. They're kind of like the classic examples. We know x squared goes up to the left and up to the right. And also, here it's going to go down to the left and down to the right. If n is odd and a sub n is greater than 0, then it goes down to the left and up to the right. Very similar to kind of like what x cubed would do, which has this shape. It's down to the left, down to the right. And on the other hand, if n is odd and a sub n is less than 0, then it goes up to the left and down to the right. Very similar to what you would see if you had negative x cubed. I always kind of like to reference it back to these ones, simply because x squared and x cubed were our parent functions from earlier in the class, and you can very quickly discover negative x squared and negative x cubed from our transformation reflection material. So whether you kind of remember the nth term test, like it is here, or whether you can compare it to a concrete example that you know how to, one of the things that we need to know is the end behavior of a polynomial. When the polynomial is presented like this in factored form, you do not have to expand it all the way out in order to find the leading term. What you can do is within each parenthesis, just delete or get rid of all of the lowest order terms and only keep the highest order term in each parenthesis. For example, out in front we have a 3x, so we keep that. In this first parenthesis, the dominant term, or the highest order term, is going to be x to the first. So I would keep that x to the first power. And within the second parenthesis, the highest power of x is the x of the first. So I get rid of everything there except for the x term. And notice that it's still being raised to the second power. If you expand out whatever's left over, 3x times that x to the second, that will give us 3x to the fourth, which is the leading term. It's a leading term where the leading exponent is even and the leading coefficient is positive, so the end behavior is going to be up and up. It's going to rise to the left and it's going to rise to the right. For finding the x-intercepts, it's the same as it's always been. You set the function equal to 0 and solve. And now we want to talk about the multiplicity. If the 0 came from a factor of odd multiplicity, like we see with these two right here, when a x-intercept has odd multiplicity, what will happen is the graph will cross the x-axis at those intercepts. If you have a 0 or an x-intercept, for example, x equals to 1, that comes from a factor with an even exponent, we call that a multiplicity of 2, or an even multiplicity. What happens to the graph in that situation is it will touch the x-axis, but it will not cross. It will actually touch and turn. Okay? So when we go to graph this thing, what you see, for instance, we said that 0 had a multiplicity of 1. What that means is that at 0, that graph will cross the x-axis. At 1, we had an even multiplicity. So that means it's going to touch and turn. So it touches and turns around. And then at x equals to 2, it had an odd multiplicity again. So that means it's going to cross through the x-axis. Simply by knowing the end behavior, the x-intercepts, and the multiplicity of each x-intercept, whether it crosses or touches and turns, that allows us to make a very detailed and rough sketch of the overall polynomial, which is something that we have to do. 6 is the same way, but in some regards it's a little bit easier for the leading term. Here the leading term is available by inspection. We just look at it. We see that it's x cubed. That's an odd leading exponent and a positive coefficient. So this one's going to fall to the left and rise to the right. Again, more practice with this, more practice graphing. The next thing we come to is an example on polynomial division. You can do this however you want, but namely, we revisited polynomial division to find zeros of functions. So usually we're going to be dividing by linear polynomials. And if that's the case, you can either do the classic long division, if you like, or you can use the faster approach of using synthetic division. The way synthetic division works is if you're dividing by x plus 3, we're essentially checking to see if x equals to negative 3 is a 0. So if you look at the factor x plus 3, it's the opposite of what you're trying to use behind the x. It's essentially what makes this term equal to 0 is the number that goes in the block here. You then need to write down the sequence of coefficients of your dividend, making sure to start with the highest power all the way down to the constant term. And if any of those terms are missing, like for example, if you didn't have, like let's say an x squared term, you would still need to plug its coefficient in, but you would need to use a 0 for that. You then perform the synthetic division process, and you want to write your answer as quotient plus remainder over divisor. We also had something called the remainder theorem, and the remainder theorem says that the value of the function c is the remainder when f of x is divided by x minus c. So instead of having to do the direct computation, which by the way, if you do that on the test, will get you 0 points. We all know how to do a function evaluation. The point isn't just to plug 3 into this. The point is that you have to use the remainder theorem with synthetic division. So I'm going to test to see if what 3 is. I plug 3 in for synthetic division. The coefficients are 12, negative 1, and 10. We perform synthetic division. It would work out being 12x plus 35, and then we have this remainder here. According to the remainder theorem, that is actually equal to the value of the function when it is evaluated at 3. So you're looking for the value of the remainder, and that's your function value. F of 3 equals 115. In question 11, we're going to use the rational zeros theorem to find a possible candidates list for rational zeros of our function. And then we're actually going to use that list to find some concrete zeros and find all of the zeros of the polynomial. The rational zeros theorem says that you want to look at the leading coefficient and the constant coefficient. The constant coefficient is 12. The leading coefficient in this case is 1. You list out all of the possible factors, let's call them P, of the constant term. The numbers that divide 12 would be 1, 2, 3, 4, 6, and 12. And then you list all of the different divisors or factors of the leading coefficient. In this case, it's just 1. And the rational zeros theorem states that the possible rational zeros of this polynomial are of the form P over Q, where P is a factor of the constant term and Q is a factor of the leading term. So you put the 1 over the 1, the 2 over the 1, 3 over 1, 4 over 1, 6 over 1, 12 over 1, etc., keeping in mind that it could be either the positive or the negative. So if we do that, we get this complete list, plus or minus 1, plus or minus 2, all the way up to plus or minus 12. And then what you want to do is kind of go through this list, picking a few values. Usually I start with 1 or negative 1, and testing to see whether or not they're actually a zero of the function via synthetic division. Once you're able to find one, then to find the remaining zeros, you just work on the resulting quotient, which in this case would be x squared minus x minus 12. And then you can continue to find the zeros of that. Here it's lucky when we get down to a quadratic that you can either factor it or use the quadratic formula once you're able to whittle it down and get to a quadratic. Same thing for the next one. The next thing we talk about is rational functions. The domain of a rational function is a collection of all x's except for those that make the denominator equal to 0. So to find the domain, set the denominator equal to 0, solve the resulting equation, and then just realize that whatever zeros you get of the denominator, those x values will not be in the domain of the function. So for this example, if you solve it out, 5/3 and negative 1 are the values that make the bottom equal to 0. So those two numbers cannot be in the domain of the function. If you wanted to go ahead then and write it out in interval notation, as we should, that's how domains are properly stated. It's everything except those 2 points. So not included, but everything else would be good. And then you can see it in interval notation. It's everything from negative infinity up to but not including negative 1. Everything between negative 1 and 5/3 not included, and then everything from 5/3 to positive infinity. The next thing we come to is vertical asymptotes. A vertical asymptote is any value of a rational function that makes the denominator 0, but also doesn't simultaneously make the numerator 0. So here, if we set the denominator equal to 0, we get x equals to 4, which is a potential vertical asymptote. A quick check, if you plug 4 into the numerator, that will give us something non-zero up top, and so that means that x equals to 4 will be a vertical asymptote. To find your horizontal asymptotes, it's a matter of comparing highest powers of numerator and denominator. There are 3 cases. If the highest power is in the numerator, then there is no horizontal asymptote. If the highest power in the numerator is exactly 1 greater than that in the denominator, we did see that we had a different type of object, which was referred to as a slant asymptote, which you would actually have in this case. If the highest power is in the denominator, then it's always the horizontal asymptote y equals to 0. And if the numerator and denominator share the same highest power, then it's the ratio of their leading coefficients. So that's how we find the asymptotes of rational functions. The last thing that is going to be on the exam is going to be a quadratic inequality or a polynomial inequality, as well as a rational inequality. Both of these are solved very similarly. You want to get one side equal to 0. Call the non-zero side your function, call it f of x. The next thing we want to do is find the boundary points in the polynomial case by setting it equal to 0 and solving. We then take those boundary points, we plot them on a number line. They will divide the number line up into a bunch of different regions. you can determine whether or not the boundary points are included based upon the type of inequality that you have. If it's greater than or equal to, or less than or equal to, then you can include the boundary points and they will be filled in. If it was a strict inequality, like strictly less than or strictly greater than, then the boundary points will not be included and they would be open circles. The next thing you would want to do is you would want to distinguish the different regions that you have. Here, 2 points will divide the number line up into 1, 2, 3 different regions. You will pick a test point within each region and take that test point and plug it into your function and see not so much what value you get out, but what the sign of the function is at the test point. That will be the consistent sign of your function within the region. And then to choose the appropriate solution set, just look at the direction of your inequality. Here, if it's going to be of the form f of x is greater than or equal to 0, greater than or equal to 0 means you're looking for the positive intervals, which in this case would be region 1 and region 3. And then don't forget to actually explicitly write out your solution set. For a rational inequality, it works very similarly. First step is get one side to 0. Let f of x be equal to the non-zero side. For your boundary points of a rational function, they come from 2 places. The zeros of f of x, which are the points where the numerator is 0, as well as the points where the denominator is 0, which is where the rational function would be undefined. For a rational function, those points that make the denominator 0, those will never ever be able to be included. So those will always be open circles. The points that make the numerator equal to 0, those boundary points, could potentially be included, again, by the type of inequality that you have. If it's less than or equal to, or greater than or equal to, then those boundary points will be included. If it's a strict inequality, like strictly less than or strictly greater than, then no matter what, no boundary points would be included, and then everything would be an open circle. Once you have your boundary points, you again do the same thing. You plot them on a number line. You pick a representative test point within each region. You take that test point, plug it into the function to see the sign of the function within each region. Here we would get positive, negative, positive. And then you look at the direction of the inequality to determine what sign you're looking for. Here, this would be of the form f of x is less than or equal to 0. So less than or equal to 0, we're looking for the negative intervals, which in this case would be region 2, which is the set from negative 5 included up to 6 not included. So again, this is what the test will look like. Those are the key things that we focused on. Good luck, everybody, and if you have any questions on any particular question or theory that we covered, just let me know.